Okay. Okay, thank you very much. Okay, we finished first the scalar part that I started yesterday, and then we go back, we finally go to the vectorial results and therefore to partial regularity. Okay, yesterday I told you, about the gradient regularity. For instance, for functionals like this, you have C1 alpha for some alpha. And in this case, you have C1 alpha for every alpha, less than 1. Okay? Now, the point is that what happens if you add coefficients, for instance? So if you add things like this and things like this. Now we go to the realm of further perturbation theory. And the perturbation theory is now intended in the following way. You know, on the very first day, I told you that how do you deal with, for instance, functionals like this? Okay? What is the Euler-Lagrange of a functional like this? This is essentially, if A is constant, this is minimizes our harmonic functions, and therefore the Euler-Lagrange equation is the following one. And the standard perturbation methods prescribe that you locally, provided that you can locally compare the solution to these two harmonic functions with a coefficient, let's say divergence of A equal to 0, where A is close to this because A is continuous. So for instance, A bar can be the average, can be the value at A at one point. And here you can do the same, but with a much more refined technique. And this is actually very non-trivial, because you see, if you start with a functional like this, then what would be the regularity of the coefficient C in order to achieve, for instance, the Hilbert continuity of the gradient? Now you see that this is intended as to be an external ingredient, and of course we expect that the dependence on these variables is Hilbert. So that would be the right continuity to expect, right? Because essentially this goes as the gradient goes. They are completely coupled. And since they are completely coupled, you don't expect that the gradient is more regular than the coefficient. On the other hand, you wouldn't expect that you really need that, for instance, C is analytic in order to just get that the gradient is continuous. But now you see one point. If this map is continuous, then there's no Euler-Lagrange equation of the functional, right? There's no Euler-Lagrange equation because this is non-differentiable. So there's in fact a theory developed at the beginning of the 80s by Evert and Giaquinta and Giusti. And this theory allows to deal with the regularity of minimizers, although you do not have at your disposal the Euler-Lagrange equation of the functional, because the Euler-Lagrange equation actually doesn't exist. Okay? You see, the Euler-Lagrange equation of a functional like this, it's formally the following: minus divergence f, and this is the derivative with respect to the gradient variable, x, u, and du, equals to the derivative with respect to the u variable, this. But if the dependence of C is Hilbert continuous, then you don't have the Euler-Lagrange equation. On the other hand, the theory invented by these people in these papers at the beginning of the 80s provides a variational perturbation method that allows to implement perturbation methods without using the Euler-Lagrange equation of the functional, but just directly using minimality. So you use minimality to make a perturbation, minimality and convexity in this case. And the result, under the following assumptions that I already wrote here, is the following one. So you get a functional, a general functional of this type, and you prescribe that the second derivatives are bounded. So you see that If f grows like p, then the second derivative k is like p minus 2. So this gives a bound on the ratio, a bound of the highest eigenvalue of the second variational matrix, so the second derivatives of f. And this provides a similar lower bound. Of course, there will be implied constants here. Okay? Under these assumptions, and under the prescription that the dependence on the lower order terms, that is the coefficients, is Hilbert continuous, so this is the modulus of continuity. This prescribes the variation, the oscillations with respect to the coefficients, then this decays as rho to the alpha. And then under this, in this case, you can essentially do the following. So how do? You take this functional, for instance, to focus on the model case, and you locally compare minimizers of those functional with minimizers of this functional. For instance, taking on a small ball, this guy, where this is the average on B rho, just to take a point, because you don't know that the solution is continuous, so you cannot define the pointwise precise representative at any point, so you replace this by the average. So you compare on small balls to minimizers of this functional, where this is the center of the ball. So you freeze the point, you freeze in the point and in the average. You take a minimizer of this functional. Now this is a constant. So this is actually a minimizer of the u to the p, trivially. This is regular, and then you implement the variational perturbation in the same type of the classical methods that lead, for instance, to Schauder estimates. In fact, under these assumptions, you can say that the minimizer of this function is as regular as the minimizer of this functional, as long as the coefficients permit. So in this case, you'll get that du is Hilbert, and is Hilbert with an exponent which is less than or equal than alpha, and less than or equal than the exponent of the p harmonicity here. And this is, let's say, a nonlinear Schauder method. So this, for the degenerate case, can be found, for instance, in the thesis of Manfredi, 86. It's a good reference, the thesis of Manfredi, if you want to know very precise estimates for the and as a JD paper, but the thesis is much better. So you should really find the thesis of Manfredi. There is the development of this method as long as the scalar case is concerned, and the estimates are very precise. You can learn from this reference. But the real thing is that essentially, once you have the regularity theory for functionals with no coefficients, then you implement the regularity theory for functionals with coefficients doing this variational perturbation method that does not make use of the Euler-Lagrange equation. Of course, this technique also extends directly to solutions to equations like this. And here you can directly use the equation, making a perturbation on the same things. So you will have assumptions like this at this stage, that a of x of u and z grows as this time as mu plus z squared, and this is p minus 1, of course. And the derivative of this guy prescribe ellipticity, and once again you prescribe the growth and the oscillations of the coefficients. So under the same assumption, solutions have Hilbert continuous gradient, and the Hilbert continuity is dictated by essentially by the exponent here. So it's a sort of nonlinear Schauder theory. So this concludes, let's say, the topic I'm going to deal with in the scalar case. Then further regularity of solutions can be obtained by additional regularity on the vector field A and on F. But essentially, as I explained to you on the first day, the focal point of regularity is C1 alpha. And after this, you can then get further regularity as long as the regularity of F or the vector field A allow by simply bootstrapping regularity. So this is very classical. So the C1 alpha is regular. And now I turn to the vectorial case. Now I turn to the vectorial case. In fact, I already wrote here capital N is equal to 1. Now capital N is larger than 1. So in this case, U, and everything is formulated in the usual way, but U is vector valued. So it's a vector valued map. Okay? It's a vector valued map. So in this case, I can tell you that the largest class of functions for which direct methods apply, and therefore for which regularity is a real instance of study is so-called quasi-convex functionals. These have been introduced by by Murray, have been studied at length by John Ball in the context of nonlinear elasticity, and there's a famous paper by Acerbi and Fusco where they provide sharp lower semi-continuity theorems for these kinds of functions. I'm not going to deal with quasi-convexity because the regularity theory is much more involved and is, let's say, it's not very much complete, but I'm going to still consider convexity. So the convexity assumptions are formulated in this way, but now the only difference is that Z is the gradient variable of a vector valued map. Okay, that's the point. Now, the main new in the vectorial case is that singularities actually occur. No matter how the functional is regular, if you take a general functional, then or a solution or an energy solution of a system, then singularities occur no matter how the integrand or the vector field is smooth. Just because you are in the vectorial case, since you are in the vectorial case, then singularities occur. Okay, main phenomenon in the vectorial case occurrence of singularities. Okay. This was first observed independently by Daejeon and Mazia. Independently around 68. And in particular, if you do consider now, if you do consider the analog of Daejeon's theory, that is, if you do consider a solution of this vector valued map with measurable coefficients, you can find solutions that are not continuous. So this was first observed by Daejeon and Mazia. Daejeon provided directly an instance of such a system. Mazia provided a higher order equation with a singular solution, with a non-regular solution. And you know that a higher order equation can be turned into a system, then you get another counterexample. So what do you get? That therefore, and later on there were other counterexamples by Giusti and Miranda. that provided an example of a system of this type, where A is now analytic in the U variable. But of course, U now appear as a possibly non-regular coefficient, so that the map looks once again as measurable and produces a singularity. This is an example by Giuseppe and Miranda. And later on, Neches gave a remarkable example of a functional which is totally dependent only on the gradient, then turned out to be to have a minimizer which is not regular. Okay, so a minimizer which is not regular. And furthermore, eventually, Yan provided an example of a functional of the following type with unbounded solutions in certain dimensions starting from 3, 4, 5. And furthermore, finally, in lowest possible dimension, there's a by Mumi and Savini. And so the outcome is that there are singularities. So now you might like to say that it's not possible to develop a regularity theory, but then another concept turns out to be the central one, and it's the concept of partial regularity. So now you say that, so the concept of the assertion of partial regularity is that after accepting that singularities occur, because they do occur actually, then you do want to say that singularities cannot occur too many times, and therefore you want to say that U is, for instance, C1 alpha under these assumptions, under the assumptions I considered before, under the assumptions I wrote at the blackboard before, but not on the whole set, because this is not possible, but on a regular set that depends on the solution itself, such that what it remains after dropping out the singular set is the regular set is a so-called singular set. Is a so-called singular set such that the measure is 0. Okay, such that the measure is 0. Okay, eventually you want to prove that the Hausdorff dimension of the singular set is less than the ambient dimension. And this actually, it's the main contribution of a large part of literature that had been developed according to the according to several authors in the 70s until the beginning of the 80s, and then under the assumptions, let me, for instance, consider systems and functionals like this. Under the assumptions you saw before, I think there are problems with the microphone, right? I mean, what happens there? Is that okay? I mean, what happens? Now it's okay. So and divergence A of x of u and du, where this is convex according to the assumptions I showed you before, and so elliptic in the gradient variable, and Hilder continuous. Hilder continuous. Alpha Hilder continuous. So under such assumptions, and in particular, we consider the assumptions before with mu equal to 1. So in particular, for instance, in the case of systems, we shall consider this assumption assumptions like this. And this is non-degenerate. This is non-degenerate. So the same happens, for instance, for the second derivatives of f when you do consider the Euler-Lagrange equation. So under this assumption, the statement is that U is C1 alpha or C1 alpha half for solutions, and for minimizers. For minimizers, you usually lose half of the Hilbert continuity outside a singular set of zero measure. So these are the two questions. The first question is to prove that this is a zero measure, and then the more delicate question of reducing the Hausdorff dimension of the singular set. So you want to say that the singular set is small beyond being zero measure. Therefore, saying that it's that this Hausdorff dimension, which is also called fractal dimension, this is a very popular, object to measure smallness of sets beyond being a zero measure. So if you want to distinguish two zero measure sets, one of the main tools is to determine this fractional dimension called Hausdorff dimension. So if the Hausdorff dimension is less than n, then this is small. The set is not only a zero set, but is zero set beyond is small beyond being just a negligible set. So for instance, the Hausdorff dimension of a line is 1, of a surface is 2, and of something which is a volume in larger dimension is 3, and so forth. And then there are, of course, Cantor sets with fractal dimensions and blah, blah. Okay, these are the two problems, and they've been solved in the vectorial case by a number of people under different conditions for systems. So I'd like to mention the contributions of Evert, Giaquinta, Modica, Giusti, Miranda. Actually, the first instance of partial regularity, not exactly under these general assumptions, is by Giusti and Miranda and Morley, Evans, Acerbi Fusco, and many others. Okay, there is actually a description of the singular set, because today we shall exploit basic techniques and ideas, essentially modern techniques ideas, because the techniques are very long, to prove partial regularity. So I would like to say that once again, all these contributions start from a seminal paper by Ennio De Giorgi for minimal surfaces, because Ennio De Giorgi proved a certain type of regularity for minimal surfaces using a local linearization method that has been eventually translated in the context of systems and functions, in the parametric context, by all these people. And eventually, after De Giorgi, there are people like Almgren that exploited similar techniques in the more general context of geometric measure theory, when instead of minimizing a variational integral, you want to minimize an elliptic integrand depending on surfaces. Okay, what is the main idea for partial regularity? It's once again the following thing. So the idea, and let me now, to better understand the issue, focus on the case p equal to 2. Okay, for the case p equal to 2. So we get a functional with quadratic growth, and which is elliptic, so therefore this is not present. It's just this one for a system. Okay, the idea is that if you take a system of this type, it's once again the idea of localization. Okay, so let me observe one thing. If you take a system of this type, which has constant coefficients, so this is a tensor which is elliptic in the sense that I, A, J, alpha, beta, alpha, I, beta, J is larger or equal than psi squared, right, for every choice of psi, then up to a change of variable, this is an harmonic map, and therefore it is continuous. So therefore you get regularity everywhere. So If you add coefficients and this matrix is continuous, then you can do the usual perturbation. Okay? And once again, it's okay. Now, the point is the following one. Now, consider a system, an elliptic system, which is nonlinear, and therefore of this type. So I will consider the case with no coefficients. So no coefficients for simplicity, just to highlight the main ideas. Now, what would you like to do with this kind of system? Okay, let's start differentiating the system. If I start differentiating the system, that is, I do usually difference quotient methods, that is, I do this and then I integrate by parts, then what I do get is the following object. Okay? And then I call this W. So I would like to prove the regularity of W. If I prove, for instance, that W is Hilbert continuous, this means that the gradient of U is Hilbert continuous. Okay, now I observe that if I freeze now at one point in the gradient variable, I obtain a system of this type. For instance, if I take a ball B rho, I do consider the average of the gradient in this ball, that is this guy, right? And then I freeze this system. I consider the frozen system in the gradient. Then I do consider this guy. And then I take a solution to this. Let me call it, how would you like me to call it? B. Now, V is regular. Why V is regular? Because now this is not a variable coefficient. This is a constant coefficient, right? It's a constant coefficient whose ellipticity properties are independent of what is inside, because are fixed by this. And therefore, I have a priori estimates for B. That tells me that B is regular. And now I remember that the basic property of elliptic operator is stability. So when two operators are close, solutions should be close. So I have that W is close to V if this object is close to this object in a ball B rho. And therefore, if V is good, W must be good too. So good estimates for B should be inherited by W. Okay? So now the whole point is reduced to understand when these two objects are close. So these two objects are close where on the ball B rho, this object, let's say the original solution, and you see this is a variable object, is close to the frozen object. Okay. Now I recall that this is usually to be assumed to be C1. A is C1, so this is continuous. So therefore, I know that these two objects are close if their arguments are close in the row. If Ux minus his average is close, is small. Okay? But of course, how do I translate this? I cannot pretend that this is uniformly close to this guy, because I already have done that U is continuous. But of course, if it is sufficient to prescribe this closeness in a way which is an average way, that is, if, for instance, this happens to be close, if happens this is small, then I can have some hope to inherit partial regularity. Of course, it is then a problem to understand when this is small. But I know that this is small almost everywhere, because almost every point is is a regular point. So partial regularity tells that if at a certain scale I am close in the mean square sense, then I will be closer and closer, and then I will get a regular point. And that's where this is coming from. In fact, I can have a description, in this case, of the so-called singular set, and this is included in the set of points such that the limit of this object is larger than 0. I know that this set is a 0 set because by Lebesgue's theory, every point is a Lebesgue point, almost every point, and therefore that's where partial regularity is coming from. So partial regularity is a nonlinear. It's a local linearization theory when the perturbation is made not in the lower order term, but in the highest order term. And since you are making a linearization in the highest possible order term, the price you pay is that you have to pretend a priori that this linearization is possible, prescribing that this is less than or equal than epsilon. So in general, there's a universal threshold such that if this happens to be small and smaller than this threshold at a certain rate, then this is becoming smaller and smaller. And so these are usually called epsilon regularity theorems. So whenever you see epsilon regularity theorems, there is this concept behind. You start with the distance which is close, and then it's becoming smaller and smaller. Philosophically speaking, this tells you that in order to produce a singularity, you have to have a certain amount of bad energy, because below a certain amount, then the ellipticity smooths that energy. That's the point. This never happens in the scalar case thanks to the maximum principle. And you remember on the first day you shrink, 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 and then you reduce the oscillations, but it might happen in the vectorial case. So in the vectorial case, you pretend a priori that this is small, so you are already prescribing a certain degree of regularity in these terms, and then this smooths out the singularity. Of course, you might wonder how you may translate an average information into an everywhere information, but this is the force of regularization techniques. You know that regularization techniques, in a certain sense, are commuting something that happens in average into something that happens everywhere. So you assume that this is small in average, and then you will prove that this is small everywhere. Why? Because in a certain sense, this will allow you to regularize more and more. And in fact, the typical partial regularity statement is made in the following way. You introduce this quantity, which is called the excess functional. So the excess functional at one point with respect to one ball is essentially the mean square deviation of the gradient from its average. And then what happens? You know that if this is small at one scale, so if there exists a ball where this is small, then this will be smaller on every ball and will exactly decay as an harmonic function does. So if you take du b tau rho, so you pass to the small scale, this will decay as an harmonic function does, so in the following way. For every tau less than, let's say, 1/2. And this is a typical property of harmonic functions. Harmonic functions have exactly this property. Once you have this, then you can prove that U is Hilbert continuous, appealing to a very useful integral characterization of Hilbert continuity due to Campanato. Campanato as Hilbert continuity characterization is the following thing. Take a function f such that this is true, so you take f less than or equal than its average. You take the average of this guy, and this decays as rho q to the alpha. So you know that a Hilbert continuous function obviously satisfies this. Because if you take f, and then you take minus the average of a Hilbert continuous function, then by Jensen's inequality, then this is less than or equal than f y, the rho, and then this is less than or equal than x minus y, and then this is less than or equal than to the alpha. So Hilbert continuous function obviously satisfies this, but the Campagnato's characterization tells you the following, that if this happens, then this implies that f belongs to C0 alpha. Why is this very useful? Because you are commuting an integral statement into a pointwise statement. Since when dealing with these kinds of problems you only have integral estimates, then this is an automatic tool that translates your integral estimates into everywhere estimates. So once again this is proved. Once this is proved, this is decaying as tau squared. You may kill this constant with a bit of this. You might iterate now, and when it's iterating, you are proving that this is decaying as to alpha. Therefore, this tells you that C0 alpha, you mean this doesn't tell you this because this is referred at one point. But you know that if this is small in one point, let's say x0, this is satisfied in a neighborhood of this point by absolute continuity of the integral, right? So if this is small at one point, you tilt a bit the point, you move around the point, and this stays small because everything is continuous here. Integrals are involved. And therefore, you are Hilbert continuous in a, let's say, in a ball, in a small ball around this point. And therefore, you have proved partial regularity. So partial regularity is a local linearization method that allows you to prove higher regularity, provided you start with the smallness quantity. And that's, this is the classical form of an epsilon regularity theorem. So an epsilon regularity theorem tells you that if you are, let's say, if you have a map, and this is not oscillating too much, let's say it's close to an affine function, let's say to the affine function that has, let's say, with this plane, if a map here, it's trapped between two planes that have orientation dictated by the average of the gradient, then this cannot suddenly do this. I mean, it has to stay close to that plane. It's getting closer and closer uniformly to that plane. So you once again see the classical effect of the elliptic regularization. Elliptic regularization is something which is commuting an average statement into an everywhere statement. Here you start from a closeness statement in average, and you commute it into an everywhere to an everywhere. Of course, you need a certain tool, a certain amount of technicalities that can be quite non-trivial to do this. But the main general assertion of the epsilon regularity theorems is the following thing. Once you are close to some sensing to an affine function, so once you are approximately differentiable in a way, then you are really good. But this has to be prescribed a priori on the contrary of the scalar case. In the scalar case, this is always the case. In the vectorial case, singularities occur, and therefore that's why you need a certain amount of energy to produce a singularity. Because if you do not have a certain amount of energy, you are trapped between two planes, then you do not have room for singularities, and solutions are Hilbert continuous, or their gradient is Hilbert continuous. So that's the main point of partial regularity. And as a matter of fact, that's how you prove that the singular set is 0. Because the typical description in the case of functionals, we know x and u of the singular set is the following one. The singular set, that is omega minus omega u, omega minus omega u, is included in the set where this is, as I told you, larger than 0. And of course, I'm restricting to the case P larger than 2. For P different than 2, there are some sort of different technicalities. And if you also prescribe that there are, this is for functionals, let's say, of this type. And if you also have coefficients, then you also have to freeze in U. And therefore, the other thing appears. U minus its average is larger than 0. So that's the main philosophical, way of thinking of partial regularity. Okay, there are now 3 standard methods for proving partial regularity. Let's say for implementing this local linearization technique. And I'm still talking about functionals that have no coefficients. So let me reduce to this case. Okay, and P equals to 2, because I'm just giving a look at a sketch of the ideas. Okay, the 3 methods, and they are essentially, they share obviously several similarities. The 3 methods are, the first is a direct method, which is the heaviest one, although it's the first one popping up in your mind. Probably. But all these direct methods are based on, let's say, on a different type of Cacciopoli inequality. So you remember that in the classical scalar de Giorgi's theory, the basic fact is the Cacciopoli type inequality. The Cacciopoli type inequality allows you to, in the scalar case, to control, let's say, the gradient be rho squared less than or equal 1 over rho squared modulo constant u minus a certain constant here, let's say u0 squared. And this is suitable to control the oscillations of u, because the gradient, dimensionally speaking, is an oscillation of u. Now you want to control the oscillation of the gradients. So you need a second type, a second order Cacciopoli inequality. The second order Cacciopoli inequality allows you to control the oscillations of the gradients around a certain point. So the oscillations of the gradient are controlled in the following way. The u minus a certain vector a, the average, is controlled by u minus u0, what you got before, minus a. Let's say you are subtracting not a constant, but an affine map. And this is once again the reverse of the previous one, because you know, this you can control via Poincaré, and the gradient of this is du, while the gradient of this is exactly du minus a. So that's a second type Cacciopoli. So this is the basic tool. All the 3 methods are unavoidably based on the use of this minimality, of this consequence of minimality. All the methods. So exactly as all the regularization in the Giorgi's theory in the scalar case follows from the first, let's say the first type of Cacciopoli inequality, everything follows from the second type. Okay, so the first, there are actually 3 methods. The direct method, actually implemented by Giaquinta, Giusti, blah, blah. Then the blow-up method, it's actually inspired by De Giorgi, as all these methods, in fact, and implemented also by several other peoples, by Giusti, Miranda, Evans, and so forth. And the harmonic approximation method, which still finds its origins in the work of De Giorgi, and then implemented by Dutzer and Grotowski in the setting of geometric measure theory, exported and also by other people. I will describe it later. Okay, I'm just giving a brief sketch of the second, giving just the ideas of the other ones. Okay, as for the first one, the first one is rather simple. The first one is rather simple. So as we said before, we take a ball, B rho, where we know that this axis is small, centered at the point x0. That will be centered at the point x0. Okay, so we consider the following functional. We take the second derivative of u, where A is the average of the gradient. Okay, what is this? This is a quadratic functional plus something which is constant and therefore does not seize the minimality, because you can translate a functional for a constant without altering the minimality, plus a null Lagrangian. So this is essentially your it's like minimizing only the first type. The Euler Lagrange equation of this functional is exactly what I told you before. It's this one. And then you prove by direct methods that du, your original minimizer, is close to the minimizer of this functional. That is the solution to this system. Why this is true? Because this is nothing but the second order Taylor approximation of your energy. So f of your minimizer must be close to g of the PDE, this type, provided, of course, what? When the Taylor approximation works. When the distance between du and A, that is this average, is small, right? And this is obtained by doing this. So this tells you that your Taylor approximation is working. Then solutions to these are good, and therefore solutions to these are good, and you make a comparison. How the second type of Cacciopoli enters? It enters in the following way. In some sense, during the estimate, you have to separate terms, and so you would need not only that this is small in L2, but this is small in L2 plus epsilon. So this gives more room for moving, right? How do you do this? How can you control the smallness in L2 plus delta with the smallness in L2? Now you take this guy, fix A, and apply Poincaré's inequality here. If you apply Poincaré's inequality, you get B rho half, du minus A, 2, less than or equal 1 half, less than or equal du minus A, 2 substar, 1 over 2 substar, E2 rho, modular constant. Where 2 substar, it's less than 2. It's 2n n plus 2. It's the number whose sublot conjugate is 2. That's Poincaré's inequality. So you can apply Gering's lemma. And Gering's lemma tells you that this self-improves up to 2 plus something. And eventually, using Hilder, you get this. So therefore, an epsilon smallness in this turns into a better epsilon smallness, and this gives more rooms to act. That's what you're doing. This requires Gering's lemma. The other two methods essentially do not require Gering's lemma. So this is a bit tougher. So the second lemma is the blow-up method, where you do essentially the same thing. But while here you do it directly, now you do it asymptotically. So this is an asymptotical linearization. The asymptotical linearization tells you the following. And this is actually a technique that it's worth looking at least once in a lifetime. For a mathematician, of course. The other normal people can completely skip it. Okay. Let me now produce a brief sketch of the proof of the blow-up method that once again uses this Cacciopoli type inequality. Oh, I deleted the Cacciopoli of second order, Let me restate it here. Okay. Now we argue by contradiction, and we want to prove that there exists a universal constant C1 such that for every tau less than this, there exists an epsilon depending on tau such that if this is true, then this is also true. And then you can iterate as before. So this is the previous statement. And now let's see how you can, in a way, linearize by contradiction. Okay, assume that this is false. What happens if this is false? Now, if this is false, there will exist a sequence of solutions, but let me call it the usual solution, and a sequence of balls and of numbers, rho m, such that this is going to 0. This is going to 0, so the axis is smaller and smaller. This, I call it Em, is going to 0. But nevertheless, you don't have this for a constant which is determined independently of everything during the proof. So let me recall that you fix a tau at the beginning, okay? You fix tau. So all these will be uniform with respect to tau, and the constant will be uniform with respect to nothing, chosen at the very end of the proof. I mean, doing this kind of fixing in a contradiction argument might be a bit scaring, but it actually works if you think better. Because the proof is rigid, all the constants are uniformly determined via estimates. Therefore, by looking at the proof, you look at the constants at the end, and then you use the proof to determine the constant at the very beginning. Okay, so this is tau m, Bm larger than certain constant that we fix at the end, tau squared, u b rho m xm. And now we start linearizing by doing the blow-up of the functions. And of course, by doing the blow-up of the function. So we determined Bm x um Bm as follows. These are centered at this. So this is rho m x minus u average in Bm. So these are the balls. We call them Bm. The balls are called Bm. And then you subtract the average, Bm, and we call these averages du Bm. So we do Am, x minus xm. Then we divide by rho m, and we still divide by the x's, where the x's, it's exactly this one. Oh, sorry, if I define the x's as tau, this should be tau. Right, this should be tau, because I take the square root of everything. This should be tau. But that's the same. You can define this like, I'm defining the x's as something that goes linearly with the gradient. So there will be a tau here, not a tau square. So if I define without the 1/2, it's tau squared, but there is no difference. Okay, anyway, what is this? This is something that very much remembers the Taylor polynomial, okay? So in fact, dBm of x is equal to du xm plus rho m x minus the gradient. Rho m cancels, and this is Bm. Now, if you consider the L2 norm of this guy, the L2 norms are uniformly bounded, because if you take the L2 norm in B1, so you see, these are maps defined in B1. So you are taking the small balls, and you are blowing up into B1. So you have a sequence of balls which are uniformly defined. You have a sequence of functions which are uniformly defined in B1. You are taking the small balls, and you are blowing up into B1. So you have a uniform, so you have a sequence of functions that are defined in B1. So what is the L2 norm of this guy? Well, the L2 norm, it's essentially the x's over the x's. So the x's, so the L2 norm of this guy is 1. And now you can, so this is, of course, the averages of these functions are 0 because of the way they are defined. You subtract always the average. This is the norm of B1. And therefore, you can extract a sequence which is weakly converging into L2. So this goes strongly in L2 B1 weakly. In L2 B1. And of course, we can also assume that these guys are converging somewhere because they are bound. And that's the asymptotic linearization. That's the asymptotic linearization. Okay, if U is a minimizer, then dm should be a minimizer of a suitable functional. In particular, it should solve the Euler-Lagrange equation of something. So let me write down the Euler-Lagrange equation of the functional. And the Euler-Lagrange equation is the following thing. So let me write down in dm. And this is equal to 0 for every phi to infinity. And by changing variables, this is nothing else but now in B1. But we want to linearize. So I subtract the null Lagrangian. Nothing happens. And I divide by em. Technicalities, technicalities, technicalities. What is this? This is the partial derivative along the direction of Vm because Em is going to 0. So you see, I linearize, that's the core of the blow-up argument, I linearize using the assumption, the counter-assumption that these guys are going to 0. I linearize using the x's. So it's an intrinsic linearization. So this goes to what it has to go, so to the second derivative of A, because this is going to 0, and this is going to A of the limit of the functions, dvm d phi. Surprise, surprise, the limit solves a constant coefficient system. So you now start understanding what is the blow-up argument. You have a sequence of bad functions. Why bad? Because they are contradicting this guy, and now you'll see, converging to something that solves something which is good, because it's a constant coefficient system. So it cannot satisfy this, and this will be the contradiction. So let me state now. Let me translate this in terms of let me translate this in terms of the function dm. If I do translate this in terms of the function dm, then I'll get that if I get tau, dvm minus dvm tau squared is larger or equal than a constant C2. Let's say C1, I called it C1, I guess, tau over 2. Now you see what happens now. If, for instance, now there are two essentially equivalent ways to go on. First way, you prove that the convergence, which is weak of the gradients, actually turns into a strong convergence. This is a natural way to do. Why? Because you know the basic property of harmonic functions. If you have a sequence of harmonic functions, you can always extract a subsequence which is converging uniformly with all the derivatives. You can prove it in a number of ways, for instance, Harnack's inequality and blah, blah. So the basic principle of harmonic functions is turning something which is weak into something which is strong. And therefore, this is the case also here, because this resembles more or less ellipticity, right? This carries over some information bearing also ellipticity. But if this is converging strongly, then this converges to V. But this is up to a change of variable and harmonic function. And so this cannot satisfy this if I choose C1 large enough, independently of everything, just by the ellipticity bounds. How do you usually prove weak into strong convergence? It's actually via Cacciopoli. But you can also now use Cacciopoli to prove this even in a faster way. You can see something which is even closer to a harmonic function. How the strong convergence of V carries over the strong convergence of the gradients in a sense. Why? Roughly speaking, what is this? Let me apply to these guys that are larger or equal than C1 over tau squared. Let me apply the second type of Cacciopoli inequality. Vm is the scaling on B rho m of this guy. So if I choose here the average of dVm and I rescale back, I'll get that dVm minus dVm tau squared is less than or equal than 1 over tau squared d m minus b m minus, let's say, the average is a of m over x minus xm. Okay, so this can be bounded. This can be bound by dm minus bm minus am squared. Okay. Okay. But now, these are not the gradients. These are the functions. They are converging strongly. Now you can pass to the limit. If you pass to the limit, you go to the lim sup. Then this is tau squared over v minus a of x minus x0 squared. But this is now, the limit is an harmonic function. So this is less than or equal than a certain constant which is universal, tau to the fourth, because you are not subtracting dB minus the gradient, you are subtracting a polynomial. So you increase the decay. So this is C star tau alpha. If you choose this C1 larger than this C star that depends only on the ellipticity, then you get the contradiction. So you see, you get strong convergence of V, but you miss strong convergence of the gradients. But the Cacciopoli inequality allows you to pass from the strong convergence of V to the strong convergence of the gradient, in a way. And that's the blow up. So you do the same thing as you did before, but you do it by contradiction, by blowing up. Sometimes this is faster. So the third method is called harmonic approximation. The third method is called harmonic approximation, and so I still have 20 minutes, let's see. So the third method is called a harmonic approximation. I will just sketch it. And it's the following thing. How do you do the linearization? The linearization is done in the following way. You take the Euler-Lagrange equation of, let's say, the average. And this is your original minimizer. And you write down as the difference minus a, and okay, this I do not have room to do this. The third method is the so-called harmonic approximation, and let me just sketch how you realize the closeness to a solution to a constant coefficient system. You get this guy. You write down, which is known to be nothing, because this is your original minimizer. You further subtract the average, because you know you have to subtract the average. And you write down in the following way, from 0 to 1, and here you use that du is solving the Euler-Lagrange equation. How do you do this? You write down the Euler-Lagrange equation, which is this one, and then you linearize this. Now, the difference between this guy and this guy is something that can be measured with this difference, which is nothing but the average. And then by a lot of estimates, by plugging out this guy, you come up with the following factor. You divide by the axis with phi in absolute value. This is smaller. That's something which depends on the axis functional times d phi. So you know that if this function would solve a constant coefficient system, this would be 0. This is not 0, because you can estimate this by the sup of L infinity, the L infinity bound of the gradient, by something which is very small, if the axis is supposed to be small. That's the car of a harmonic approximation. So you see that you can simply write down this guy as this guy using the Euler-Lagrange equation. Therefore, you can estimate this by this object. This is less than small, using something that gets small when the argument is small. And now this is small. And now you use the harmonic approximation of the judge. It tells you the following thing. If you have a map that satisfies this property, so if this map fails to be harmonic by a certain delta, then if delta is small enough, this is really strongly close to be harmonic, in the sense that for every epsilon, there exists delta, such that if this holds, then there exists a harmonic function such that this is close. And this is another form of linearization. This other form of linearization allows you to say, once again, that if you are distributionally close to a harmonic function, you are strongly close to a harmonic function. So this is a way to say that you are close to being a harmonic function in the sense of distributions. Because if you would be a harmonic function, this would be 0. Now this is not 0. This is close to be 0. Now if this is close enough, you are strongly close to be harmonic. Of course, this is not sufficient enough, because you don't need that the functions are close, but the gradients are close. But once you know that the functions are close, you can once again use Cacciopoli to commute these into a gradient deformation. So this is the third form of linearization, which is intermediate between the two, because the first is direct, the second is indirect, and this is partially direct or indirect according to your taste, because then the proof of this is done by contradiction. But at the end, the essence is always the same. You fix an average. You show that you are close to a solution to a constant coefficient system. then you first show this at the level of functions, and then you bootstrap at the level of the gradient using the Cacciopoli type information. I think I still have 10 minutes. Right. Okay, these are the three methods: the direct method, the indirect method, and the blow-up method, and the harmonic approximation method. And when you go to problems with P growth that can be also degenerate, and I'll lately tell you something briefly of that, then there's another statement, there's a theorem due to Dutzer and myself, and this is, I think, 2002 on Calc Bar, I guess, no, 2004, 3, 4, I mean something, 2003, 4, I don't remember exactly. That tells you exactly the following for the P Laplacian system. So you get, if you get of course, one thing, here you need, I forgot an important thing, you need to bound the energies, otherwise you cannot go on by contradiction, because you want to go by contradiction. This is satisfied by the fact that you are getting du minus A over the excess, which is bounded exactly as in the blow-up arc. Okay, so this tells that for every epsilon larger than 0, there exists delta such that if this holds, then there exists a true solution of the P Laplacian system such that u minus h to the p is less than 1, and du to the p is less than or equal than a universal constant c. So that's the P harmonic approximation, and this is suitable to deal with problems with P growth. The proof is again by contradiction, but it's much more delicate because you have to deal with the nonlinearity and you have to pass to the limit in the nonlinearity. But essentially, this is the same thing. And so this is called the P harmonic approximation. It's proved several years ago. I think it's in 2004, I guess. 4 on Calc Bar. Okay, and now, what about the singular set? So as I told you, okay, I think that, let me just close this information with this information about the singular set. Now, you know, after partial regularity, you know that the solution is regular outside a negligible singular set, which is a closed subset with 0 measure. And now you want to prove that this is small beyond being just negligible. And okay, and now you have functionals like this. And you have the singular set which is 0 measure. So the problem has been remained open for surprisingly many years since partial regularity was established. I think in a paper that was issued in the 81, and so this was the only result available at that time. In fact, it is stated as an open problem in all these papers by Jacquint and Giusti and all these books and blah, blah. And only in 2006, we were able to give an answer with Christensen and myself. There's a paper in ALMA where we prove the following result, which is probably let's say which also involves other tools. But let me state the following result. So the main idea, and this will be the object of the first topic I will deal tomorrow, is the following one. So what remains which is global beyond singularities in the vectorial case? As I told you before, it remains the higher integrability. So once you have this functional with p growth, let's say f x du less than or equal, let's say, z to the p, L z to the p plus 1 and p. Let me just take for simplicity p larger or equal than 2, but for p less than 2 you can do similar things. Then you have partial regularity on one side, which is this one. And on the other hand, the only result you have on the gradient, which is global, is that du belongs to LQ for some q larger than p. This is Gering's lemma. This is the last result I told you yesterday. This is the only thing. And this is true independently of everything, even if x, the dependence on x is measurable. Okay, what we were able to prove with Christensen is the following result, is that the dimension of the singular set, so the Hausdorff dimension of the singular set, is less than or equal n minus the minimum between alpha and q minus p. And so in particular, it's strictly less than n, where alpha is the Hilbert continuity with respect to the two variables, and q is this higher integrability exponent. So that's the estimate we had with Christensen. It's one of the several estimates I'm going to talk about tomorrow. Tomorrow I'll talk about this singular set reduction and other things that can be done. In particular, we also proved a sort of dual differentiability version of Gering's lemma, because we proved that if you call this, let's say, how would you like to call delta? We proved that du belongs to W sigma p over p for every sigma less than delta. So we proved the fractional differentiability result. So that was this, let's say we turned the higher integrability of the gradient into a higher fractional differentiability of the gradient. And tomorrow I will briefly mention fractional solvable space. And then from this, we solve this long-standing problem of the singular set of the Hausdorff dimension, getting an estimate which is explicit in the sense that this is totally independent of the solution, but it only depends on this q that depends just on the ellipticity bounds of the functional, so it's universe. So I think today we can stop right now.